Okay, today we're looking first of all into the mechanical work and then into the energy. So mechanical work or just work. And meaning of the work in physics is different from the meaning in the everyday life. Because in everyday life you can do like different kinds of work. In physics it has strict definition. If we have, let's say, some object and we apply force F, and using this force we move this object by the displacement will be S in displacement, then mechanical work equal force times displacement times cosine angle between them. Fs times cos theta. Why we need multiply by cos theta?
To get the angle of the slope.
Because does the whole force move in the
Some of
object?
the gravity takes away.
Gravity, because only horizontal component of the force will be moving the object. Only this component, which is F cos theta, that's what's moving object. So that is what is mechanical work in physics. And it's measured in joules. Unit of measurement of work is joule. Now, if I, for example, I'm pressing on this table as hard as I can, am I doing any work?
Yes.
No.
What is the displacement?
No.
What displacement is it? If this table has any displacement? No.
So work is zero.
So work done zero. I apply force, but because there is no displacement, there is no work done. To do work, I need to make displacement. So, for example, if I leave this chair, yeah. Now, at this instance, am I applying force?
Yes.
Because I need to help. Am I doing any work?
No.
No. But if I moving it, I'm doing mechanical work. Because there is a force, there is displacement. Now, if I, question? If I will be pulling this chair along the floor, but applying force not horizontally, I'm pulling it horizontally, but I'm applying force at the angle. Will all my force do work? No, only horizontal component. Vertical does not do any work because we don't have any vertical displacement. Now, energy. When we're talking about the energy, using word energy a lot in our life. Energy. What is energy? What does it mean if we say the object has energy? What does it mean?
Potential energy.
It could be potential energy, but what does it mean?
Power.
It means object can do work. If object has energy, it means it can do work. Now, sorry, can I ask you to bring, like, can you go to office? There are under my table, there are two basketball balls. Can you bring? So, there are three types, there are many types of energy, but in motion, there are three types of energy. There are three types of energy. There is one type of energy we already introduced, talking about elastic inelastic collision, and that was what kind of energy we introduced when we were talking about kinetic energy. So first type of energy we introduced was kinetic energy. Thank you. So what does it mean if saying when object, object has energy, it can do work? For example, if this ball, no, it's the camera or not, I have ball here. And this ball, second ball, is that's fine. Second ball will have potential energy because it has height. When I move it, I give it some energy. Now it has energy. So I'm saying it can do work. If I will release it, this ball can move this ball, so can do work. So if I release it, this ball can move that ball, and it's done work. That means this ball had energy. And one type of the energy that we discussed was kinetic energy, which equal, what's the formula for kinetic energy?
MV squared over 2.
Mass times speed squared divided by 2. This related to the motion. If object moving has kinetic energy. If one ball flying and hit another ball, it can move, it can do work. We throw this ball and hit that ball, it will have kinetic energy and it can do work to move the second ball. So it can do work, it has energy. Second type of the energy is gravitational potential energy, which related from the gravitational. What gravitational? It so due to the gravity, and that energy any object have if we lift it up, if it has height. So equal mg times height. Now, question. Let's say mass of this whiteboard marker, let's say to make it more simple, 100 grams, so 0.1 kilogram. M equal 0.1 kilogram. Now G, to make it more simple, let's take 10 meters per second squared. And let's say height of this table is 1 meter. H equals 1. And if I put this marker on this table, what will be its gravitational potential energy?
110. 1.
Okay, one question, answer 1, 0.1 times 10 times 1 will be 1, and I'll say 0.
Yeah. 1.
Yes? No?
I have a question. What is JP?
Acceleration due to the gravity. That when you will be running your teeth and you're falling down, that will be your acceleration. Now, and both answers are correct. 1 is correct and 0 is correct. How it can be? How it can be that both answers are correct? Relative to what? From where we measure the height? For gravitational potential energy, we need to decide what we take as 0. Relative to the floor, it will have its 1 meter above the floor, it has energy. If it falls from the table, it can move something, can do work. But what its height really, when it's on the table, what its height above the table? 0. Can it do any work? No, because height equals 0.
Sure.
So, even more, gravitational potential energy can be negative. Let's say height from here to the ceiling is, let's say, 3 meters. So then energy of this will be negative 3 joules. What does it mean negative? Gravitational potential energy negative 3 joules.
Opposite direction.
energy doesn't have direction. Now, let's say this ball has, relative to the floor, let's say 2 joules of energy. When I release it, it will, by itself, I'm not throwing it, it will fall by itself and can do work. It has to do. But if I release it, can it get to the ceiling by itself?
No.
We need to do work to lift it there. That's why it's negative. Because we need to put some energy in. By itself, it cannot go up. So gravitational potential energy can be even negative. All depends where we take zero. Make sense? Gravitational potential, we need to decide from where we measure height. Height above what? Ground, this floor, ceiling, table, whatever. And usually when we will be solving problems, the most convenient way will be take height as the lowest level in that particular situation. And the third type, yes?
So does that mean in gravitational pull questions there's an answer and it's always also zero? Or is that like it's an answer and zero? Or no?
No, because
No, but,
as well, you don't know.
No, but the question will not be asked what is its gravitational potential energy just that. Then if question like that, it's incorrect question and you can give any answer.
Is it infinite answers? Because you couldn't go infinite like heights?
Yeah.
No, or I will say, no, not infinite, but generally saying we can say about infinite formula, yes. Now, and the third type of energy object have is, mechanical energy, is elastic potential energy. When we stretch or compress the spring, it equals K. Remember Hooke's law? The K is a constant there, spring constant, times X, which is extension, change of the length of the spring, squared over 2. That is elastic potential energy. If I will take spring and stretch it and release, it can do work. You can hit something and do work. Yes.
What's K? Oh wait, never mind. What's X? Extension.
Extension of the spring. Or compression.
What's
Okay.
Reminding about the Hooke's law. F equal when we have spring and we stretch it. The X will be changing the length of the spring. We pull it, we stretch it. And the relation between the extension of the spring and the force, F equals Kx. K is a spring constant. It's characteristic of the spring. It tells us how many newtons we need apply to stretch the spring by 1 meter. That was the K. Now, so there are 3 types of mechanical energy. And now we can give second definition of the work, that mechanical work is a change in energy. Mechanical work equals change in energy. Because I can do work on this ball, I'm doing work on it. I'm lifting it up. I'm doing work and I'm increasing its energy. If I will release it, what will happen with its energy? With its potential energy? What will happen with its gravitational potential energy if I release it?
It goes down.
It decreases. Potential energy is decreasing. So it will be doing work. I'm doing work, ball can do work. So change work is a change of energy. We can increase the energy of the object, giving it energy, doing work on it, or object can do work and lose energy.
Where does the energy go when we lose it?
Now we are right coming to that. The energy never disappears, never created, it's always constant for the closed So we have, together with the law of the conservation of the momentum, law of the conservation of energy is one of the most fundamental laws of the nature. That the total energy, which will be, when you consider only mechanical processes, will be sum of these three, mv squared on 2 plus mgh plus kx squared on 2 will be constant. Energy of the system stays unchanged. For example, two examples. If we have a ball with a mass, let's say 500 grams, 0.5 kilograms, and it has initial height of, let's say, 2 meters. First, as I already gave height, so we take 0 somewhere below. What is its gravitational potential energy of this ball? What will be its gravitational potential energy? Using formula, gravitational potential energy equal mgh 0.5 times 9.8 times 2 will be equal 9.8 joules. Will be 9.8 joules. So 2 meters, it has 9.8 joules. When I release it, when it's hit the floor, what will be its gravitational potential energy? 0. But the same energy will not disappear. What happens with this energy?
It goes to the ground.
When it's falling, what happens with its speed?
It goes down.
Increases.
Its speed increases, so it's kinetic energy. When it will be falling, its gravitational potential energy will be turning into kinetic energy. Will be turning into the kinetic energy. So we can find what will be its speed. Because energy should be the same. So its final energy still has to be 9.8. mv squared on 2 has to be equal 9.8. Energy stays the same. Energy just can transform from one type to another. In this case, from gravitational potential to kinetic. So let's find that speed. We will have v squared will be equal 2 times 9.8 divided by 0.5. That will be 39. This is 39.2, I think. And we take square root, so will be approximately something like 6.25. Can you check with the calculator?
6.26.
Pretty close, 6.26 meters per second. So we use law of the conservation of energy. Initially it has gravitational potential, then it turns into the kinetic energy. And one more example. Is this, did I make mistake calculating this?
No.
This is v squared from here, 2 times 9 divided by mass is 0.5. And that is v squared, so we take square root then. Make sense? Now another example. Let's say we have compressed the spring. We have a spring with a spring constant of 100 newtons per meter. K equal 100 newtons per meter. And we compress that spring by 20 centimeters. So X equals 0.2 meters. Don't forget, you always need to turn things into meters, kilograms,
Seconds.
Joules.
seconds, yes. Now, And we attach to that spring, we attach the ball with a mass 50 grams. And then we release the spring, and spring pulls the ball. So we have ball on the table. So we have there we have a ball and we have spring which we compressed. We hold it, compress it, we have a ball, and then we release the spring, and it's of course extended to its original weight and push the ball. What will be the speed with which ball will leave the spring? What will be the speed with which ball will leave the spring? What energy system has when it's compressed? What type of energy it will have? Elastic potential energy, which equal kx squared on 2. So here we have elastic potential energy equal kx squared on 2 equal 100 times 0.2 squared
0.1 meters per second.
divided by 2 equals what? Will be equal, that will be 0.04, will be equal to joules. Will be equal to joules. What will happen with this elastic potential energy when spring extended and push the ball?
Goes into the ball.
Into the
Kinetic.
kinetic energy of the ball, which will be equal mv squared on 2. So 0.05 times v squared on 2. And according to law of the conservation of energy, all elastic potential turns into the kinetic, so equal to joules. So from here we can find now speed of the ball. So you get v squared will be equal 2 times 2 divided by 0.05, which will be equal 18, I believe. And then take square root, v will be equal 8.9 meters per second.
Yeah.
Yes?
Doesn't like a fraction of the energy go back into the spring because the spring recoils?
Yes, very good observation. But it's not, because spring will be actually, when it's extending, if we like completely disregard it, we will not take that into account. But spring will be actually move, not just extending, but it's moving, so it will have some kinetic energy as well, which then turn into its elastic potential of its little bit extension beyond its original length and then turn to the length back. So it will not affect this calculation. Now, where, let's say, if this ball now will be rolling along the table and table has friction, rough table, and the ball stops, it's rolled like 5 meters along the table, and it stopped. What happens with this? It has 2 joules of energy, and it stops. Where does energy go?
Into the table.
What kind of energy?
Gravitational force.
This table will be lifted when ball rolling along it?
It's
Kinetic
friction.
energy.
It's friction.
It will be lost due to the work done against friction. And what it will do when you have friction, if you take 2 objects that start, for example, rub one against another, what you will feel?
Heat.
So it will turn into the heat energy. It will not disappear energy, but it will turn into the heat energy. Let's find what the friction force is there. How we can find it? All this energy will go on the work against friction. work equal Fs, because force N, in this case, force will be along the table in same direction as the displacement, so we will have 2 joules equal F times 5, so friction force will be equal 0.4 newtons. So that's introduction to work and mechanical energy, and we will be working on the questions now. Like, subscribe, and donate to help fight Russian fascists.